Yesterday I have spoken about electrodynamics of conducting moving matter and some aspects of the dynamo problem. Today I will switch to the mean field electrodynamics. We start again with our basic equations, which I explained yesterday. But we consider now situations in which the velocity and then also the magnetic field possesses complex geometrical structure and complex time behavior, so that it makes no longer sense to follow up these fields in detail, but it is reasonable to look for mean values. And we define mean values in the following way. We split any field, consider first a scalar field f into a mean in the fluctuating part. And the mean part is defined by some averaging procedure. We don't fix this averaging procedure in detail. We consider many different procedures in this theory, but we require that they satisfy exactly or approximately the so-called Reynolds rules. First is the distributive property of averaging in that sense. The second is the statement that twice averaging is the same as one average, which is equivalent to the statement that the fluctuations vanish under averaging. The third rule is you can pull out from the averaging procedure mean fields in that sense. This is equivalent to this average over f bar averaged and g bar averaged is just, you can forget the averaging bar here, and also this statement, if you have a fluctuating quantity here, then this average vanishes. The fourth rule is that averaging commutes with differentiation with respect to time or with respect to space. A very important consequence of these rules is if you average a product, fg, then this average is not simply f average, or mean f times gf, but there is an additional term that is the average over the fluctuations. This is a term which is important for all mean field theory as soon as you have nonlinear terms. And we apply this to the 2 Ohm's law, where we have u cross b, and then this applies there. If I said we consider a scalar field, I understood this in a general sense, not as a contrast to pseudoscalars, just a one-component quantity. We define vector fields, mean vector fields, by averaging the components with respect to a given coordinate system. In that sense, the average of a vector field depends on the coordinate system. And this applies analogously to tensors. I use both notations, f bar and f in angle brackets. I think I should write down these rules again so that you have it for comparison. R 1 is f plus g average equals f average plus g average. R2 is twice averaging is the same as simple average. See, R3 is f average g is g average, and the fourth rule is df over dx average equal to df average over dx, and so on. Okay, I give a few examples. You can think of a statistical example. Average, that means you imagine many copies of the object considered, and you average over these copies. So, for example, if you speak about the convection zone of the sun, you consider many suns, maybe an infinitude of suns, all with the same basic setup, so geometry and boundary conditions and so on, but with different realizations of the fields, say different distribution of the pressure also. And you level these different copies by a parameter, say Q. Here it is Q is considered as a continuous parameter, and you take a normalized distribution function, and then you define the average in this way. Then, fortunately, all four rules here are satisfied. It is a big advantage of this kind of average, but it is not clear from the very beginning what is the relation between the so defined averages and observable quantities. We assume as a rule that this average is the same as a space or a time average, but it is an open philosophical question. Okay, you can avoid these difficulties and take just a space average defined in this way, again with a normalized distribution function, which we consider as symmetric in psi. Then the first rule is automatically satisfied. The last R4 is satisfied. You can interchange integration with a differentiation. Differentiation with respect to a parameter which is not the integration variable. I must take the other one. But these rules, R2 and R3, are not generally not satisfied. They can be justified as an approximation if there is a scale separation, so that you have, say, length scale in the spectrum of the length scales, a gap. You have here the small scales, here the large scales, and your averaging scale, given by G, is in the middle. Then you can justify these rules as an approximation. You can consider special cases. Here, G is chosen as a box function, and Rechteck function. Box function. And here I integrate only over one variable. You can define this average in this way, or you can average over two coordinates, like here. In the limit of length L tends to infinity, then all rules are again exactly satisfied. Then the averages no longer depend on this coordinate, and they are satisfied. In many cases we have used this average. Okay, other examples.
Carpenter.
Yeah?
With this box averaging, then you don't need space separation, or you still do? Scale separation.
No,
Then you don't need
I
scale
have
separation.
the keyword scale separation here, and not in this is special case. No, you don't need it. And with box function, I mean this. Okay.
Then an average of an average is not the same.
Sorry?
An average of an average is then not the same.
The average, yeah. R2. It is not the same, not automatically the
So
same.
box average,
In the case of the box average, at least in the limit of averaging over all the coordinates, say over all x or all y,
then it's okay.
then it is satisfied.
Yeah.
Okay, I spoke about statistical and space averages. You can define time averages in the same way. It is completely analogous to the space average. And again, these rules R1 and R4 are exactly satisfied. The two other rules not automatically, again, in the case of scale separation. We speak in this case of a two-scale situation. Example, two-scale turbulence or something like this. There are still other possibilities. You can consider the
The previous slide.
previous, yeah. For example, in Baginski's theory of the almost symmetric dynamo, he used the azimuthal average. Think of, say, spherical coordinates or cylindrical coordinates and average over all values of phi, as said here. Then you have this azimuthal average, and since the average itself no longer depends on this coordinate phi, all the rules are satisfied exactly. The big disadvantage is this average is automatically axisymmetric. If you want to treat a model of the Earth also, a dynamo model of the Earth, you have then only axisymmetric magnetic fields. You cannot discuss the case of oblique magnetic field. This is a big disadvantage. The advantage is that the rules are automatically satisfied. Okay, sorry, I forgot this. Yeah?
With these Reynolds rules, suppose some of them are not satisfied. Does it make progress impossible or complicated? Because, okay, fine, they are not satisfied, I will derive for a given type of averaging the corresponding rules and they will continue.
That's what I said. Under certain circumstances, for example, scale separation in space or in time, you can justify these rules as an approximation.
But suppose that they don't apply. I can derive from the other rules which apply to a given type of...
I think it's nothing to do. And you cannot apply this average, or at least what I will tell you later doesn't work. We assume the exact or approximate validity of these rules. Okay, I already mentioned time averages. These are not all examples. You can, for example, define an average by filtering a spectrum. So represent your quantity f as a Fourier integral with a Fourier transform f hat and exponential of I kx. You can do it also with the time. And then you can say, okay, my average is this integral, but only over the small k. That means over the large scales. And in this case, 3 of these rules are satisfied, but R3 is not satisfied. It can be justified as an approximation again if you have a separation of the wavelength. By the way, you can rewrite this to a space average, use the convolution theorem, then you can write it in a form function of x plus xi times a function of xi, the weight function, and this corresponds to a special case of space average, or if you do this with respect to time of time average. Okay. You may imagine one of these averages in the following derivations. Return to our basic equations and put B equal to B bar, average B plus fluctuation, U bar plus fluctuation, and so with all the other quantities. Then take the average of the original Maxwell equations and you get this. This means you get just the Maxwell equations again for the mean fields. Formally, completely the same. The difference is in Ohm's law. You have here U cross B, and the averaging gives not simply U bar cross B bar, but an additional term, U cross B fluctuations averaged. And that is a big difference. You have in Ohm's law an additional electromotive force. Perhaps you remember what I said yesterday. I wrote sometimes a term E external in Ohm's law, and I said it can, for example, describe the effect of a battery. And it's just at this place I have this mean electromotive force formed with the fluctuations of U and B. You can take these equations and can derive the mean field induction equation, where you have here again this E, or you can also average the original induction equation and arrive at the same result. These are the mean field equations.
Karl-Heinz, I mean, just a question of language. Historically, why do people call this an electromotive force? Because it's like it's an electric field.
It is not exactly an electric field. If you think of the electric field which occurs in the Maxwell equations, then this term doesn't belong to the electric field.
But it has the same dimensions as the electric field.
It has the same dimensions. It has the same dimensions. I call it electromotive force, an effect which can drive a current. In this field, in this case, a mean current. The name is related to the mechanical force, which I would call a ponderomotive force.
A comment regarding the averages. I was about to ask whether it is necessary to have the same definition of the averages for the mean field and for the EMF, and of course the answer would normally be yes. Yeah. But one of the big disadvantages of an azimuthal average was that you cannot consider non-axisymmetric magnetic fields.
Yeah.
But the EMF would still be, you expect this to be independent of azimuth on the average.
That's not necessarily. It depends on which average you have in mind. Take a simple space average
but
or
the
time average,
the turbulence you would
it can well depend on
it can technically, yeah. But I mean, you would not expect it to be, and then it would make sense to calculate this EMF. I mean, there's no preferred longitude a priori, unless you postulate that or assume it.
I'm not sure that I understood you well, but you can think of any average here, not necessarily on an average over phi, and then you have these relations. And then also E can depend on all three space coordinates and on time.
Yeah, because the mean field. Yeah. Because the mean field depends on that. Yes.
Yeah.
But your question was, if you did the azimuthal average, then you can't describe non-axis symmetry, and that's correct.
That's then still correct. Yeah.
I didn't. Maybe you are right, but I did not.
He repeated basically what you said.
Huh?
He just repeated what you said, that you cannot describe non-axis magnetic fields.
Sorry, I have sometimes difficulties with my old ears. So, the central, this electromotive force E is the central quantity in all mean field electrodynamics. And you have seen that the basic equations look like the usual Maxwell equations, and Ohm's law differs only by this electromotive force. And the crucial point, the crucial issue, is to elaborate this electromotive force. Okay. We have this equation for the fluctuations of B, small b. You can take the original induction equation and put B equal to B bar plus B dash and U equal to B bar plus B dash, and you can subtract from them the averaged mean field equation, which I have shown on the slide before, and then you get this equation for the small b, for the fluctuations of b. U cross b in brackets dash is an abbreviation for this. These are the fluctuations of U cross b. Yeah, you subtract from this the mean value here, and so these are just the fluctuations of the cross product U cross b. So this is the equation which determines b. I have written this equation so that I have, if I would put 0 here, I have a homogeneous equation for small b, and then I have inhomogeneity. So I can write the solution in this form. B0 is a solution of the homogeneous equation, and BB is a special solution of the inhomogeneous equation. I imagine that I have chosen such a solution which vanishes for B equal to 0. So, both parts, say, the part B0 is a functional of the quantities you see in the equation, small u and u averaged. B is a functional of the three quantities, u bar, and b bar from here. And it is linear in b bar if you consider it as a functional of these quantities. If you multiply small b by a factor of, say, 2, and b bar by a factor of 2, then the equation is again satisfied. That's why it is linear in B. So, now calculate the average of U cross B. It has again two parts. One with UB, U cross UB average. I called it E script E0. And another formed with B, with a subscript B bar. So The first term is independent of B bar. The second term is linear and homogeneous in B bar, if we consider the small b as linear and homogeneous in B bar. Okay, consider this second most important term here. It depends on u, small u, and u bar, and linearly on b. That means you must be able to write it in this form. It is not here not the result of some derivation, but it is just the statement that it is linear and homogeneous, and here is some function of u and u bar. And if you think of say turbulence, then you have the situation that the correlation between quantities in 2 points is only unequal 0 if the 2 points, space or time, are not too distant from each other. That is, that this kernel, which depends on psi and tau, vanishes for sufficiently large psi and tau. Of course, EB depends on the behavior of B, then in some surrounding given by like C and tau, of the point for which you consider the electromotive force. Okay. Once more, you can represent the part B in this way, and if you write it in the induction equation, you get this. These are the old, the familiar terms. Here is the EB, and here I have written the E0. It is again an inhomogeneous equation for B, as the homogeneous part is linear, because this integral is linear, and I have an inhomogeneity given by the quantity E0, which doesn't depend on the magnetic field. Okay. Now remember what I said, that the correlation, or simply that, excuse me, I will start here. We will, at the moment, assume that B decays to 0 if B average is equal to 0. That means B0 decays away. So we have not to deal with B0 and with the consequence E0 of B0. We consider only the BB which leads to EB, and then this electromotive force can be represented in this general form. Assume now that B varies only weakly in space and time. Then you can, in this integral, this Bj represent by a Taylor expansion. I have written down only the first 3 terms. And if you put this in this integral, you see that your E takes just this form. Tensor Aij times Bj, third rank tensor Bijk times the derivative of B bar, and the same with the time derivative of D. And you see immediately that these quantities Aij, Bijk, and Cij can be represented with this K. Very often, this relation, this was the relation I had on the previous slide, is replaced by a relation without the time derivative. If you read papers, you have sometimes the feeling this is the electromotive force in mean field theory. But you should be aware that this relation is an approximation in the way which I have shown you, and you are obliged to check it for any application, to make sure that the terms which you have here cancelled, the time derivative of B and the higher space and time derivatives are not important. This is very, very important to have this in mind. Again, sometimes when reading papers you get the feeling this is the original relation. It's not true. Okay, this relation reduces then the mean field induction equation to a second order parabolic differential equation. Here I have these terms with Aij and Bijk written in a symbolic form. It is just the same type of equation as the original induction equation. And that is a big advantage of making this ansatz. But this ansatz is not general. Nevertheless, we accept it for the next considerations. Okay, I will give a few examples. For this purpose, I define symmetry properties of turbulence. When saying turbulence in this context, I simply mean a fluctuating velocity field, regardless whether or not it has special properties of turbulence, developed turbulence, or something like this. It's only a name for fluctuations of the velocity field. We call a turbulence homogeneous if all quantities which depend on u are invariant under the translation u goes to u, or u from x and t goes to u from x plus delta x with t. That is the definition of homogeneity. You have to consider all possible mean quantities which depend on u, and they must have this property. We call a turbulence steady, or to be more precise, statistically steady, if this invariance applies under the time shift. We call a turbulence axisymmetric if this invariance of our mean fields applies under rotations of the velocity field about a given axis. We call it axisymmetric with respect to a given axis if this is invariant under rotation about this axis. We call a turbulence isotropic when this applies for all axes. Isotropic in a point if it applies for all axes running through this point. And at the end, we call a turbulence mirror-symmetric or non-helical with respect to a given point or a given plane if this invariance applies under reflection of u about this plane or this point. A reflection of an object, or say you may have in a turbulent field structures which you can classify as right-handed or left-handed. So, for example, you find in a turbulence a flow like this. It is right-handed. You can have a flow like this. This is left-handed, and you can have a distribution of such structures. If you have mirror symmetry of the turbulence, then there is an equipartition of the right-handed and left-handed structures. If you consider this structure, so for example this, in a mirror you see a left-handed structure. If you consider a screw in a mirror, this is a right-handed screw, you see a left-handed screw, and vice versa. So mirror symmetry excludes the preference of one-handedness in the turbulence. It doesn't mean that you have no such structures, but you have an equipartition of the right-handed and left-handed structures. So that is usually in the laboratory homogeneous isotropic turbulence is at the same time mirror symmetric. There must be special circumstances if you have no mirror symmetry. Okay. Let's consider a simple example. We consider a homogeneous isotropic turbulence. We leave open whether it is mirror symmetric or not. We assume again that we have this representation of the electromotive force. Again, it is an approximation. We assume that the turbulence is homogeneous, and from the homogeneity we conclude that these coefficients A, I, J, A, B, I, J, K are independent of the position. If you shift the velocity field, then these quantities, which are mean values, don't change. You conclude from the isotropy that these Aij and Bij are isotropic tensors. And let it explain a bit more in detail. If you calculate the Aij with a given velocity field in a given coordinate system, you can rotate the velocity field around about an axis, and this should not influence Aij, because I assume isotropy. You can now turn the coordinate system in the same way. Then you have, with a new rotated velocity field in the new coordinate system, exactly the same situation. That means the components of Aij must be the same. The components which you calculate in the original system with the original velocity field and in the rotated system with the rotated field. So that means that the tensor Aij must have the property that its component representation is invariant under a rotation of the coordinate system. We call tensors who have this property isotropic tensors. And it is a simple exercise to show that the only isotropic tensor of the second kind is a constant times the Kronecker tensor. And in the same way, you can show that the only isotropic third rank tensor, all what I said is for Aij applies analogously to B ijk. It must have this structure. It must be proportional to the Levi-Civita tensor with some scalar function beta. So if you put this into this representation of the electromotive force, you see that it takes this form. E is alpha times B bar minus beta curl E bar. So very simple structure of this electromotive force under these simple assumptions. You can put it into Ohm's law. You have Ohm's law. Average Ohm's law is sigma E average plus E. We have no U bar. Put this E in this law. Then you have also a J on the right hand side, and you can arrange it this way that Ohm's law has this form, where sigma is sigma m, should mean field is sigma over 1 plus mu sigma beta. We call this the mean field conductivity. The mean field induction equation takes this form. There is originally a term curl E, and if you replace it in this way, you get this term with the alpha coefficient and this here eta plus beta, and this is the, I call it eta m, mean field diffusivity. Yeah, the mean field induction equation takes this simple form in this example. I will show you on the next slide that alpha changes its sign if you reflect the velocity u at a plane or a point, whereas beta remains unchanged under this reflection. You would conclude from this sign change of alpha that alpha must be 0 in the case of mirror-symmetric turbulence. If your turbulence is mirror-symmetric, you have no such alpha term. The occurrence of this term is called alpha effect. Okay, look at the next slide. We start again with this relation, and we recall that this relation is just a consequence of the induction of the equation for the small b. Just this way. Here is this the fluctuations of u plus b. We consider this relation at the point x equal to 0 and write it in this form. This is just E, just the definition of E. I have indicated with alpha that it depends on u, and beta depends on E. Here is E averaged at the point x equal to 0, and here is curl B at the point x and t. Now, remember what I told you yesterday about the symmetry properties of the Maxwell equations and the induction equation. If this equation 2 is satisfied with the set u, e, b bar, then it is also satisfied with a set u reflected, b reflected, b bar reflected. It is most convenient here to consider a reflection at a point, then this reflection is just defined in this way. The reflected field U is minus U with the argument minus x and k. Okay, then in addition to this relation, we must have the same relation with U, B, and B bar, replaced by U reflected, B reflected, and B bar reflected. I have written this here. I have already replaced the U reflected and the B reflected here by these expressions. The minus, the two minus with U and B cancel each other. Here, this minus is from the reflected B. I have the reflected B bar replaced by minus B bar and so on. And this minus results from this. And here it is the same. It is again an exercise to show that curl of U cross B reflected at the point x equals 0 is equal to curl of B bar. Maybe I should give an explanation. If you start with, consider for example the Z component of this. It has a term T B reflected. I only x. Z component, Y component differentiated with respect to x minus. Okay, I will not write all this. Then replace this by minus b of minus x and incorporate the minus here. Consider this at x equal to 0, then it is just dB over dx. And that's the reason why I could replace this term, where I had original reflected, by this term without reflected. Now, consider that this relation exists. It is trivial if you think of statistical averages or time averages. Then at the point x equals 0, you have here 0, here minus 0, which is equal to 0, and here also 0. And so it is a bit more complicated in the case of space averages. But you can again, it is an exercise to show that also in this case it applies. And if you then compare these two relations, you find that alpha for the reflected field is minus alpha for the non-reflected field. And B for the reflected field is equal to beta, B for the reflected field. So that is what what we had on the previous slide. Alpha changes sign under reflection of U, beta not. So in the case of mirror symmetric turbulence, alpha is equal to 0. Okay. We know some properties of alpha and beta, but we would like to know how alpha and beta depend on detail on the velocity field. And it means we should calculate alpha and beta. And here I introduce, it is in general, you have to solve the equations for little b. And this solution is in general not easy because you have here in addition the term which I denoted by bracket u cross b bracket dash. And it is easy to solve this equation if you have this term cancelled. And this is just what we call first order smoothing approximation for or second order correlation approximation, so-called. It's just that this term is cancelled. A sufficient condition is that b is much smaller than b1. Kando yesterday explained that many situations are just the opposite, that the fluctuations are much larger than the mean values. But we search where we have light, and so we consider first this situation, which can be treated in the framework of the second order correlation approximation. Another remark, if we put b equal to 0, this equation describes the decay of b. So we have no Cohen solutions, according to our assumption we made earlier. I explained to you yesterday how you can solve an equation of this type. We had here b, and on this side the curl of E external. How you can solve these equations with the help of a Green's function. And we apply this mathematical method, which I explained yesterday, to this equation, and we can write the solution b in this form. This is the anyway decaying initial condition. And if we form now u cross b with this solution, we find that E, the I component, the I component of u cross b, can be written in this form with a kernel which contains this Green's function and the correlation of uk at x and t and ul at x minus psi t minus tau. So I said before that a representation of E in this form is just possible by logical reasons. Here I have shown in a simple example that you can derive really such a relation with this kernel. Okay, I could now, by the way, this result applies independent of homogeneity and isotropy of the turbulence. I could now take this relation and calculate from this the coefficients alpha and beta. But I will proceed in another way. I will consider simple limiting cases and not start with this. And okay, this is the equation for the second order correlation approximation. We assume that we can characterize u by a characteristic velocity u, that we have a characteristic length of u, the correlation length, and a characteristic time of u, the correlation time. And we define a parameter q, lambda square c over eta t. That means lambda square over eta is the decay time of a magnetic structure with the characteristic length lambda c, and this is the ratio of this decay time and the characteristic time c. This quantity is just good for an approximation of the importance of these two terms in this equation. The ratio of these terms, the magnitudes of this term is just q. We define in addition a Struhal number in the usual way and a magnetic Reynolds number in the usual way. By the way, if the Struhal number is exactly 1, then the parameter q is just the magnetic Reynolds number. So we consider two cases. First, the case where q is much bigger than unity. It happens, for example, if eta tends to 0, and then we speak of high conductivity limit, but this notation high conductivity limit is a bit misleading because it can also happen for very small tau c with a finite eta. And the other case is small q, low conductivity limit, but the same comment, a q can be small not only if eta is large, low conductivity limit, but also if tau c is large, if we have a more or less steady turbulence, not statistical steady turbulence. So these are the two cases which we will treat, and in one case we have this equation, and the other case we have this. We start I made a mistake. Sorry. Yeah. We start with the first case. We have this equation. We can express sufficient condition, not necessary condition for the validity of this equation by Struhal number is much smaller than unity, and there's no restriction to the magnetic Reynolds number. We ignore, just for simplicity, any time dependence of B bar, and so we can then write the solution of this equation in this way. This is again the initial condition, and this is the other solution. Having this available, then you can form U cross B average, which is E, and then we obtain for the Aij and Bijk just these expressions. By the way, the electromotive force here, E, contains from the very beginning no higher derivatives, space derivatives of B. And it's just the property of this high conductivity limit. We have not neglected them. They don't occur here. So, consider now again homogeneous isotropic turbulence. That means we have these relations, alpha ij is proportional to the Kronecker tensor, and so on. We can derive from them alpha is equal or 1/3 the trace of Aij and beta follows this relation, and then we can calculate alpha and beta, and we obtain this result. Alpha is an integral minus 1/3, an integral, and here is u, and the curl of u, but this at the time t, and this at the time t minus tau, integral tau. Often it is written in this form, where this characteristic, or this time tau c alpha is just defined by equating these two two expressions. And then alpha occurs as a quantity which is determined by what we call kinetic helicity, U curl U. And for beta we have this relation. Okay, we will not discuss so much about alpha, beta. Beta is given this way. It occurs in the mean field conductivity, and consider, just to have an example, the solar convection zone, and I just will play with numbers here without saying that these are really the correct numbers. This is the conductivity and the eta for the solar convection zone. As a characteristic velocity, I take 200 meters per second. This is velocity which occurs in the granules. Lambda c is again a characteristic length for granules, and tau c is the lifetime of granules, say 5 minutes, 3 times 10 to 2 seconds. If I then calculate my parameter q, I find a number bigger than 10 to 6. That means I'm really in the limit of large q. The Struha number is 1/10. So that we could say that the approximation we have made here is still justified, and we can calculate from those that we have a Reynolds number of this order. Then calculate this B over eta, and then sigma m over sigma, the mean field conductivity compared with the original conductivity, is a value in the order of 10 to minus 4. That means the mean field conductivity is much smaller than the original conductivity. This is an estimate which is of interest in view of, for example, the lifetime of sunspots. If you calculate the lifetime of sunspots with this value of sigma, then you get very, very large times, and you come to reasonable times, months or so, if you take sigma m instead of sigma. Okay. Consider the other limiting case, the low conductivity limit. We have then this equation. The condition for validity is that the magnetic Reynolds number is small, and if we uncurl this equation, we have this. And here is a gradient, which we don't need. Remember what I told you about Biot-Savart's law. Biot-Savart's law was derived from an equation curl of B equal to mu times current. And I explained to you that in the current I can cancel any gradient. And so I'm not interested in this gradient. I just put this part of, say, the current into the relation, into Biot-Savart's law, and I have then this relation for small b, and I can calculate the electromotive force. Okay, it is again a simple exercise to form U cross B and to calculate this expression, which applies not only for homogeneous isotropic turbulence. You can expand E under this integral in this way. This is the same procedure as I did before, and you get then a representation of the mean electromotive force in this way, and with these values for the Aij and Bij. Again, we return to homogeneous isotropic turbulence. Then all averages are independent of x, and we have this, again, these relations for alpha and beta. And what we find is this: we have now an expression for alpha, where we have again u, curl u, but now u at a point x, and curl u at a point x plus psi, and this is integrated in a certain way over psi, and for beta corresponding relation. We can represent alpha also in another way, express the velocity field by a vector potential and a scalar potential in this way. Psi is the vector potential, phi is the scalar potential, and assume that we have this relation for the vector potential, and assume further that the averages of psi and phi are equal to 0. If you, maybe I should jump to the next. This is take the curl of this relation, then you have curl u is equal to curl psi, this vanishes. That means you find Laplacian psi is minus curl u. And this is what is written here, is again a Poisson equation, and you can write the solution in this form. Remember this when I return to the previous slide. We have just this expression is a representation of alpha, and so you can represent alpha in this way. It is just the average of u times vector potential psi, or you can write it also in this way. You can replace u in this way, and you can show that the term originating from phi vanishes. So you get a result for alpha which is independent of phi. That means independent of compressibility. Phi describes the compressibility. And in a bit more complex way, you can derive such relation for beta. This is insofar interesting. If you have the incompressible case, phi doesn't occur, phi can be put equal to 0. And then you have here the proof that beta is positive. Beta is positive, at least in the incompressible case. It can be, can take negative values in the compressible case. Okay. Okay, only a short remark. You can consider arbitrary Q, you can return to the relations I have shown you before, and then alpha takes this form, Green's function, and here the helicity spectrum, correlation of U with curl U, but this taken at x and t, and this taken at x plus psi by t minus tau, and a similar relation for beta. It is often said in papers that alpha is the helicity. And it is very dangerous to say this or to think this. You see, it has something to do with the helicity spectrum. But you cannot say that in general alpha is the helicity. With some weighted average over the helicity. Okay. I have shown you all these derivations in physical space. You can do all the same also in the Fourier space. You can use this Fourier transform. The advantage is firstly that you have algebraic equations instead of differential equations, and so the calculations could be easier. And you have a theorem, you have always this correlation tensor. And there is an interesting theorem about its Fourier transform. This is a Fourier transform of this, and you can show that for homogeneous and statistically steady turbulence, Buchner's theorem applies. That means this quantity is positive, or this Fourier transform is positive definite in that sense with any vector x, and you can draw far-reaching conclusions about the sign of beta also with this theory. Okay. Yeah.
So the compressible case where beta was can be negative, cannot be covered then with Buchner's theorem.
No, cannot be covered.
And why was that?
It is why as well possible that beta is negative, but no case is known where beta m that is omega, let's say eta m is eta plus beta. No case is known where this would be negative. So this can be negative, but not more negative than this. There are many such cases are investigated. We will not go into details. Okay, the headline of this lectures is mean field dynamo theory. So far, in mean field electrodynamics, I have not spoken about dynamos. And I remain with homogeneous isotropic turbulence, and I write down the induction equation as I explained, which I showed you before. And I look now for solutions of this type and ask whether they can work. And okay, write this in this equation, and then you find that for the quantity b hat introduced here, which depends on k, no, it doesn't depend on k. You have just this equation. If you take a coordinate system, a Cartesian coordinate system in which k has only a z component, then you can write these equations in this form. You conclude that b hat z component is equal to 0, and the other two components satisfy these equations. And non-trivial solutions of these equations exist just when the determinant is equal to 0. Determinant equal to 0 means just this, or you can express it in this way. If you have no alpha effect, you have decaying solutions, because eta m, look at this, is always positive. But if you have an alpha effect, p could be positive. There are cases where it is more negative, but it could be positive. Non-decaying solutions are possible as soon as you have alpha bigger than eta m times k. So you can, if you have the infinite space, you can always have a big wavelength, that means a small k, so that this is satisfied with an arbitrarily small alpha. And so you have always, in an infinite space, growing solutions, maybe with large spatial scales. If you no longer consider the infinite space, it is not so. It is some inconsequence to consider a fluid sphere which is surrounded by free space. We have spoken only about homogeneous isotropic turbulence, but let us simply do it, and it has been done, for example, by Vogtmann. Write down the induction equation inside this fluid sphere, in this way. Outside you have curl B equal to 0 and divergence B equal to 0, or what is equivalent. B is a gradient of phi, and phi satisfies the Laplace equation outside. Assume, we spoke yesterday about this, that the magnetic field is continuous across the boundary of this fluid volume. Assumes that the magnetic field vanishes sufficiently strong with radius tending to infinity. You can define a parameter R alpha, which is related to the magnetic Reynolds number. Alpha has a dimension of the velocity. And then, if you make this ansatz, you can reduce this to an eigenvalue problem for P, which depends on R alpha, and you see that non-decaying solutions, I forgot to mention R is the radius of the sphere. And you see that non-decaying solutions exist as soon as R alpha exceeds a certain value, 4.49, and it's just a zero as a function. And the most easily excitable mode is of dipole. Right. This was has been investigated a long time ago, and later, and this solution exists also in the limit of eta of high conductivity limit. I have just I have shown how quantities like alpha and beta look like in the high conductivity limit. They have values which are different from 0 and quite normal values. That means that such a solution should also exist for the high conductivity case, and also in the case of infinite conductivity. This solution continues in outer space, and it grows endlessly in outer space too. And this is, of course, in conflict with the Pondy and Gould theory. Pondy and Gould, the Pondy and Gould theory says that the outer field is bounded, cannot grow endlessly. And this was a conflict which was discussed 2 decades ago by Moffat and others. And the resolution is that this model is not quite correct insofar as we have homogeneous turbulence everywhere in the sphere, and then no longer in outer space. But you cannot have in a sphere everywhere homogeneous turbulence. So at the boundary, the radial component of the velocity must be zero. And it is in contradiction to the assumption of homogeneous isotropic turbulence. And I then modified this model with another expression for the for the electromotive force, which considered a spherical symmetry and the correct behavior at the boundary of the sphere, and then indeed this conflict disappears. You can have a dynamo inside. It is in a sense a hidden dynamo, but it doesn't. The magnetic field doesn't penetrate the surface, so this conflict is removed. Yeah, I think I should.
So,
yeah.
why doesn't magnetic, I mean, physically, why it doesn't penetrate?
Sorry, why?
I mean, how does it resolve itself? What happens at the boundary? So the field grows inside, and then what happens?
You just see that the field is, if it is initially zero at the surface, it remains zero at the surface. Just because you have not, you have no longer this, but you have a more complicated law, which contains, by the way, 9 coefficients instead of this 4. Here, homogeneous turbulence is assumed, and you have to assume spherically symmetric turbulence, and then you have no longer this solution, but you have a solution which vanishes at the surface. You may have a dynamo inside. It is a hidden dynamo.
So is there a clear difference in the magnetic field structure between that solution that you have and that where you have a perfect conductor as a boundary condition? Probably not. This, no. They look very similar.
Look very similar.
But they are different, of course, the boundary conditions. Mm.
Okay.
But in a perfect conductor, you would probably have a surface currents, right?
Perfect conductor. Oh.
But you don't have a surface current, yes. I think that's the difference, yeah. You don't have a surface current in that solution.
But even in the case of the perfect conductor, these coefficients, and also the coefficients in the also more general ansatz, are unequal to 0. Yeah, I think the time is nearly over.
Yes, there could be questions, of course.
Continue tomorrow.
So, thank you. And other questions? Maybe one question concerns the issue of the scale separation, which is often brought up as a major critique to mean field theory. And of course, we don't actually know of any situation where the lack of scale separation has really been an actual problem, where it's confirmed as a problem. I don't think we know of any such cases. Because whenever one wants to check mean field theory, it either does work, or if it doesn't work, then it's not because of the lack of scale separation. So
you have also the excuse you can take an average also, which is not dependent on,
yes,
on the scale. scale separation.
Right. So it's often overquoted or overstated, this requirement. I should maybe emphasize.
Yeah.
Hello?
Yeah, I mean, in that context, I think there are 3 scales. I think we want to discuss things like this. Because if there is this random stuff going on with helicity, random flows are there with helicity, automatically you will get a random field which has got a scale not necessarily of the system and not of the forcing.
Yes.
Something in between. And then you will also get a scale of the system. So there is never any scale separation.
I mean, the velocity, that's right. Yes.
If the velocity is helical, there is never scale separation of the field. So I think it's just something which you have to live with. I think. The other comment I had is that you kept emphasizing that Q, taking limits in Q is different from taking limits in Rm.
Yeah.
You should call it low and high conductivity. But if in a system the stall number is of order unity,
Yeah.
then these two become the same, right?
Yeah. If it is exactly unity, then Rm is equal to Q. Yeah.
Or even if it's off order unity kind of stuff, because in most turbulent systems, the stall number is not very much different from 1.
Yeah.
It is not very small compared to 1.
Yeah.
In that case, the 2 limits become Rm limits in magnetic Reynolds numbers.
That's true.
And in that case, we'll have all our headaches of the small scale dynamo.
Yeah.
Okay.
Just to go further on that one, I mean, your estimate for the Stroll number was a 10 in the solar convection zone. Yeah.
Sorry?
In the granulation there,
Yeah, yeah.
Stroll number. If you go deeper into the, what happens to the Stroll number then? Does it go back to being order 1? I mean, as Kandu says, in most turbulence, most convective turbulence,
Absolutely, you know it.
you usually get.
My idea is also that the Stroll number is always in the order of unity.
Yes.
Yeah.
But first of all, the Stroll number should be defined, I mean, we know this empirically at least, should be defined with respect to the wave number,
Yeah.
which means that his Stroll number would actually be 2 pi always.
Okay, yeah.
And then it's 2 pi everywhere.
Yeah, so it is in fact order 1. Yeah.
For MHD turbulence, we have checked that numerically. And then it's independent of depth.
Yeah.
So actually,
But
I
the
also
2
don't-
pi results from the definition of the Stroll number.
Yes, yes. Yeah, right. Okay, if there are no further controversies at this point, we should of course have the coffee.